Welcome guys and welcome for a new year. I hope you're ready for this year. Senior 3 syllabus is talking about 5 units. The first unit is talking about the transition elements. Unit 2 is talking about the analytical chemistry. Unit 3 chemical equilibrium. Unit 4 electrochemistry, and Unit 5 organic chemistry. Now let's start with chapter 1, transition elements. The number of transition elements exceeds 60 elements, which means that they represent more than half the number of the known elements till now. The transition elements are divided into two main categories. The first one is main transition element, and the second is inner transition element. Only the main transition element will be discussed this year. If you notice, this is a sample for the periodic table. The elements which are found in the middle, which are transition elements, Dblock elements, and the inner transition elements are F-block elements. In this year, we're going to study the main transition elements only. The main transition element or D-block element, the D-block contains 10 vertical columns. Why? Because of the gradual filling of D sublevel with electron. This D sublevel consists of 5 orbitals, which can take up to 10 electrons. The letter B characterizes these number of D-block groups except group 8th group, which contains 3 vertical columns. That's because they have the nearly similar in the chemical and physical properties. For example, in the fourth period, we have iron, cobalt, and nickel. All of those have nearly the same physical and chemical properties. And the electronic configuration for this element, group 3b, is Ns2 n-1d1. Group 4b, Ns2 n-1d2. Group 5b is Ns2 n-1d3. Group 6b is Ns1 n-1d5. Group 7b is Ns2 n-1d5. Group 8, the first one is Ns2 n-1d6, Ns2 n-1d7, Ns2 n-1d8. And 1b is Ns1 n-1d10, and group 2b is Ns2 n-1d10. So this is the electronic configuration, the general electronic configuration for these groups. Okay, the transition elements is divided into four main series. The first one is the first transition element series, which starts from period 4. Starts with scandium and ends with zinc. After that, the second transition series starts with deuterium and ends with cadmium. The third transition series starts with lanthanum and ends with mercury. The fourth transition element starts with actinium. The first transition element series, in which a 3D sublevel filled successfully, and it's located in the fourth period. It begins with scandium with the electronic configuration 4s2-3d1 and ends with zinc. The electronic configuration is 4s2-3d10. The second transition series, in which 4d sublevel is filled successfully, it located in fifth period. It began with deuterium. Its electronic configuration is 5s2-4d1 and ends with cadmium. Its electronic configuration ends with 5s2-4d10. The third transition series, 5d is filled, located in the sixth period, begins with lanthanum and ends with mercury. The fourth transition series, in which 6d sublevel is filled, is located in the seventh period. The first transition element starts with scandium 21, Sc21, titanium, Ti22, vanadium, V23, chromium, Cr24, manganese, Mn25, iron, Fe26, cobalt, CO27 nickel, Ni28 copper, Cu29 and zinc 30. So are these elements are important for economy? Yes, the economic importance for the first series elements. Although these elements form less than 7% of the weight of the Earth's crust, they have a great importance. For example, scandium, for example. What about its properties? Scandium is found in very small amounts spreading on the large area of the Earth's crust. And its use is to make an alloy with aluminum to form MiG fighter jets. This is because adding a little amount of scandium to aluminum, it forms an alloy characterized by lightness and high hardness. Scandium and mercury, for example, used in making mercury vapor lamps, used in TV photography at night to produce light with high quality look like the sunlight. Titanium element, for example, its properties, it's a strong element of a rigidity of steel, but it less dense than steel. Titanium maintains its durability at high temperature. It's used in making an alloy with aluminum to make aircraft and space shuttles because it maintains its durability at high temperature, while aluminum, its hardness decreases when it used individually. It's used in dental implant and artificial joints due to the rigidity. It's not rejected by the body, inert substance, which doesn't cause any poisoning. The most famous or important compound for titanium is titanium dioxide, which is used in some protection cosmetics because nanoparticles prevent the effect of ultraviolet rays on the skin. After that, vanadium. Vanadium is used in manufacturing of car spring because on adding a small portion of vanadium to steel, a very hard alloy is formed, which has the ability to resist corrosion. The most important compounds for vanadium is vanadium pentoxide, which is used in manufacture of dyeing and ceramics and glasses, and it's also used as a catalyst in preparation of sulfuric acid, for example, by contact process or manufacture of strong magnetic conductor. What about chromium? Chromium resists the effect of atmospheric air, rusting and corrosion, despite being chemically active element, due to the formation of a non-porous metal oxide on its surface, in which the volume produced of oxide molecules is larger than the volume of metal atoms. This layer prevents the continuity of the interaction between oxygen and chromium. And it's used in plating and leather tanning. The most important compound of chromium is chromium trioxide, used in manufacturing of dyes, and potassium dichromate, which is used as an oxidizing agent. Manganese element. Manganese is Mn25. So the properties of manganese, it's very brittle metal in its pure form, so it always used in alloy or compounds. For example, ferromanganese alloy, which is composed of iron and manganese, used in railway tracks because it's harder than steel. Aluminum manganese alloy, which consists of aluminum and manganese, used in manufacture of soft drink vessels, cans, as it resists corrosion. The most important compounds of manganese is manganese dioxide, which is used as a strong oxidizing agent in dry cells, used as a catalyst in decomposition reaction of hydrogen peroxide. Potassium permanganate, for example, used an oxidizing agent as antiseptic substance and used as an antiseptic substances. Manganese disulfate, which is used as fungicide. The next element is iron. Iron element used in manufacture of reinforced concrete, electric pylons, knives, surgical tools, magnet, guns, and cannon pipes. And also iron used as a catalyst in, for example, hopper push method to prepare ammonia gas from its elements, and Fischer-Tropsch method to convert water gas, mixture of hydrogen and carbon monoxide gas, into liquid fuel. Cobalt, for example, this is the 7th element. Cobalt is CO27. Its properties is similar to iron in magnetic properties because because of them can be magnetized. Both of them can be magnetized. The uses of cobalt. Cobalt is used in manufacture of magnets, and dry batteries used in modern cars. Most important isotope of cobalt has 12 radioactive isotopes. And the most important one is cobalt-60, which is used in detection of the quality of industrial products, like detecting of the cracks and welding connections. This is number one. Number two, diagnosis and treatment of tumor. That's because cobalt-60 isotope produces gamma rays which have high penetrating power. After that, nickel element, which is 8th element, Ni28. The properties, its shiny appearance. Nickel steel alloy are characterized by their hardness and their high resistance to rusting and acid corrosion. Nickel is used in manufacture of nickel-cadmium battery, which can be charged. Nickel is used in metal plating to protect these metal from oxidation, rusting, and to give them the pure appearance. Divided nickel is used as a catalyst in hydrogenation process of oils. Nickel-chrome alloy are used in heating coils and electric furnaces because they resist corrosion even on high heating till redness. The 9th element is copper, which is Cu29. Copper is considered to be the first discovered metal. Copper-tin alloy are known as bronze steel. Copper is used in manufacture of electric cables because it's good conductor of electricity. It's used in coins industry. The most important compound of copper is copper disulfate, which is used as a fungicide in purification of water and insecticide. And Fehling solution. Fehling solution is a solution which is used in glucose detection, where it's a blue color. It changes by the effect of glucose of sugar into orange color. After that, we have the last element in the first transition series, which is zinc, Zn30. Zinc is mainly used in galvanizing other metals to protect them from rusting. Galvanization, it's the covering of a metal surface with a layer of zinc to protect them from rusting. The most important compound of zinc are zinc oxide, which is used in manufacture of paints, rubber, and cosmetics, and zinc sulfide, which is used in manufacture of illuminating paints and X-ray screens. Let's talk about the electronic configuration of these elements. The first transition series elements are located in the 4th period after calcium. So the 5 orbitals of 3D sublevels in this element are filled successively by a single electron first until manganese Mn3d5. Then the pairing of electrons takes place till zinc Zn30, which ends with 3d10. And here we have the electronic configuration of these elements. But notice, in this electronic configuration we have 2 exceptions. The first one is chromium and the second is copper. Why we have an exception in those cases? First, if we make the electronic configuration for manganese, the normal electronic configuration for chromium, for example, we have argon 18 4s2 3d4. Argon 18 4s2 3d4, we have the stable state of any element that its outermost energy sublevel is half filled, completely filled, or empty. If we notice, we have 4s2 3d4. If we transfer an electron from 4s to 3d, the electronic configuration will be 4s1 3d5. 4s is half filled, 3D is half filled, so this is an unstable state for chromium. By the same idea for copper. Copper, the electronic configuration, the normal electronic configuration will be 4s2 3d9. If we transfer an electron from 4s to 3d, the electronic configuration becomes 4s1 3d10. The 4s is half filled, 3d is completely filled, and this is a stable condition. So don't forget, the atoms more stable when it has low energy. When does it happen? It happens when the atom has the outermost energy sublevel is half filled, completely filled, or empty. So it's generally noticed that the atom of iron of transition elements is more stable D sublevel, completely filled with electron as D10 or half filled as D5. For example, we get copper ion, positive 1, zinc ion, positive 2. All of those are stable conditions. Half-filled electrons like chromium atom, manganese ion, positive 2, ferric ion. However, the half-filling or complete filling of 3D sublevel is not the only factor that causes the stability of the electronic configuration of the compounds. Let's talk about the oxidation state of the first transition series. And it's known that the 4s sublevel is saturated by 2 electrons, and 3d is saturated by 10 electrons. And both 4s and 3d are close energy level. So when an atom of the main transition element is oxidized, the electrons of 4s sublevel are lost firstly, because they are farther from the nucleus than 3d. After that, began to lose the electron of 3d to give the oxidation state shown in the following table. For example, we have scandium had the oxidation state of only positive 3. Titanium, for example, had 2, 3, and 4. Vanadium, 2, 3, 4, 5. Chromium, 2, 3, and 6. Manganese, 2, 3, 4, 6, 7. And this manganese had the highest oxidation number. After that, we have iron and cobalt had 2 and 3 oxidation states. Nickel has 2, copper has 1 and 2, and zinc has 2. From the previous table, all elements of transition have the oxidation state positive 2 after losing the 2 electrons of 4s, except scandium, which has only oxidation state of positive 3. This is because as we said from a while, this is because that 4s sublevel has near energy to 3d sublevel. This is number 1. Number 2, the oxidation state increases from scandium to manganese, which had the highest oxidation state of positive 3 in group 5b. After that, the oxidation state decreases gradually to become again 2, positive 2 for zinc in 2b. The highest oxidation state of any element doesn't exceed the number of each group. So copper in the first transition series, silver in the second transition series, gold in the third transition series. Most of transition elements are characterized by several oxidation states, as we say, due to the successive loss of electrons from the 2 sublevel ns n-1d, which are close in energy. Representative elements mostly have only one oxidation state, unlike the transition elements. Ionization potential of the first transition series element atoms increases gradually in case of successive oxidation states. That's because of the successive loss of electron from the 2 sublevel 4s and 3d, which are close in energy, leading to the increase of the effective nuclear charge, and consequently the increase of the nucleus attraction force to the valency electron. So the ionization potential increases. What about the successive oxidation states? For example, if we have vanadium, which have the electronic configuration 4s2 3d3, it needs 648 kilojoule per mole to oxidize vanadium to positive 1. And vanadium positive 1 needs 1364 kilojoule per mole to oxidize positive 1 to positive 2. From positive 2 to positive 3, it needs 2858 from kilojoule per mole. From positive 3 to positive 4, it needs 4643. For positive 4 to positive 5, it needs 6523. So as the oxidation numbers increases, the value of ionization potential increases. In representative metal like sodium, manganese, aluminum, it noticed that the increase of the second ionization potential of sodium than the third ionization potential of manganese. And the fourth ionization potential of aluminum is very high. Why? Because to make the aluminum positive 4, we have to break a complete energy level which require a very high ionization energy. And in the following table, we have the ionization potential for aluminum, for example, to aluminum positive 1, we have 578 kilojoule per mole. From positive 1 to positive 2, we have 1811 kilojoule per mole. From positive 2 to positive 3, we have 2745 kilojoule per mole. From positive 3 to positive 4, we have 11,540 kilojoule per mole. Hence, the transition element can be defined as the following. Transition element is an element which has an incompletely filled D or F sublevel, either in free atomic state or one of its compound, one of its oxidation state. Don't forget, the transition element generally has incompletely filled D or F. Main transition has incompletely filled D. Inner transition has incompletely filled F. Excellent. Thank you for your